There are a number of devices that can be used to detect the particles and gamma rays emitted when a radioactive nucleus decays. Such devices detect the ionization that these particles and photons cause as they pass through matter. The most common kind of detector is the Geiger counter, which the figure shows. The Geiger counter consists of a gas-filled metal cylinder. The alpha, beta, and gamma rays enter the cylinder through a thin window at one end. Because of their higher energy, gamma rays can also penetrate directly through the metal. A wire electrode runs along the center of the tube and is kept at a high positive voltage, around 1000 to 3000 volts, relative to the outer cylinder. When a high-energy particle or photon enters the cylinder, it collides with and ionizes a gas molecule. The electron produced from the gas molecule accelerates toward the positive wire, ionizing other molecules in its path. Additional electrons are formed, and an avalanche of electrons rushes toward the wire, leading to a pulse of current through the resistor R. This pulse can be counted or made to produce a click in a loudspeaker. The number of counts or clicks is related to the number of disintegrations that produce the particles or photons. The figure shows a scintillation counter, which is another important radiation detector. This device consists of a scintillator mounted on a photomultiplier tube. Often the scintillator is a single crystal, like cesium iodide, but plastic, liquid, and gaseous scintillators are also used. In response to ionizing radiation, the scintillator emits a flash of visible light. The photons of the flash then strike the photocathode of a photomultiplier tube. The photocathode is made of a material that emits electrons because of the photoelectric effect. These photoelectrons are then attracted to a special electrode kept at a voltage of about plus 100 volts relative to the photocathode. The electrode is coated with a substance that emits several additional electrons for every electron striking it. The additional electrons are attracted to a second similar electrode with a voltage equal to plus 200 volts, where they generate even more electrons. Commercial photomultiplier tubes contain as many as 15 of these special electrodes, so photoelectrons resulting from the light flash of the scintillator lead to a cascade of electrons and a pulse of current. As in a Geiger tube, the current pulses can be counted. Ionizing radiation can also be detected with several types of semiconductor detectors. Such devices utilize N and P-type materials, which we studied in section 23.5, and their operation depends on the electrons and holes formed in the materials as a result of the radiation. One of the main advantages of semiconductor detectors is their ability to discriminate between two particles with only slightly different energies. A number of instruments provide a pictorial representation of the path that high-energy particles follow after they are emitted from unstable nuclei. In a cloud chamber, a gas is cooled just to the point at which it will condense into droplets, provided nucleating agents are available on which the droplets can form. When a high-energy particle, such as an alpha particle or beta particle, passes through the gas, the ions it leaves behind serve as nucleating agents, and droplets form along the path of the particle. A bubble chamber works in a similar fashion, except that it contains a liquid that is just at the point of boiling. Tiny bubbles form along the trail of high-energy particles passing through the liquid. Paths revealed in a cloud or bubble chamber can be photographed to provide a permanent record of the event. The figure shows a photograph of tracks in a cloud chamber. A photographic emulsion can also be used directly to produce a record of the path taken by a particle of ionizing radiation. Ions formed as the particle passes through the emulsion cause silver to be deposited along the track when the emulsion is developed. As one example of radiation detectors, here is a Geiger counter connected to a Geiger-Müller tube in a pancake probe geometry. The thin covering over the probe allows it to detect alpha, beta, and gamma particles. When turned on, you will randomly hear clicks every so often. This is due to the background radiation from cosmic rays that travel through the Earth's atmosphere. Let's put the Geiger counter probe near a more active source. Back in the mid-1930s, a brand of dinnerware was produced under the brand name of Fiestaware. The Fiestaware plates and bowls were coated with a ceramic glaze that gave them brilliant red, yellow, and orange colors. The glaze also contained uranium oxide, which is radioactive. Placing the probe near the plate reveals the elevated activity from the glaze. The primary constituents of the radiation coming from the glaze are alpha particles, as the uranium-238 undergoes alpha decay into thorium-234, and beta particles, as the thorium-234 and protactinium-234 in the decay series undergo beta decay. A thin sheet of lead blocks almost all of the radiation.